Welcome back to educator.com, and thank you for joining us for linear algebra. Today we're going to be discussing solutions of linear systems, part 2. Okay, let's go ahead and get started. We closed off the last session by converting the following matrix, and you'll remember, of course, sometimes I actually leave off the little brackets on the side of the matrices simply because it's a personal notational preference, that's all, as long as you understand which grouping of numbers goes together. Okay. We had 1, 2, 3, 9, 2, negative 1, 1, 8, and 3, 0, negative 1, 3, and we converted that to reduced row echelon form to 1, 0, 0, 2, 0, 1, 0, negative 1, and 0, 0, 1, 3. And notice the reduced row echelon form, it has 1 as leading entries, and wherever the row has a 1 that is a leading entry, everything else in that column is a 0. This column, of course, doesn't matter because it's the third row here, so it is irrelevant as far as the definition of reduced row echelon is concerned. Okay, now we did that just for matrices. Well, we already know that a given matrix represents a linear system of equations. So this system looks like this in terms of the variables. X plus 2y plus 3z equals 9. Notice x plus 2y plus 3z equals 9. And then 2x minus y plus z equals 8. And then 3x plus 0y. You don't necessarily have to put this there. I like to put it there simply because for me it keeps things in order, in line, and it just keeps things consistent. Minus z is equal to 3. And again, what we've done is whenever we transform a matrix from the standard matrix to its reduced row echelon form, we form an equivalent system. So what we've produced is the following. This time I'm going to actually avoid the zeros. We have x equals 2, y equals negative 1, and z equals 3. So this is our solution. Matrix represents the linear system, converted to reduced row echelon form. We get, that's one of the reasons why we like these 1s in these positions and zeros everywhere else, is because it just gives you the answer. X is one thing, y is another, and z is another. Okay. And in this particular case, we have a solution, so it is a unique solution. For this particular system, for this particular system, there is no other. It is unique. Okay. Let's take a look at another example. Let's actually go ahead and explicitly give the linear system this time, and then we'll just deal with the matrix. So we have, let me write the system up here. We have x plus y plus 2z minus 5w is equal to 3. We have 2x plus 5y minus z minus 9w equals negative 3. We have 2x again plus y minus z plus 3w equals negative 11. And we have x minus 3y, excuse me, plus 2z plus 7w is equal to minus 5. And again, I think the biggest problem that you're going to run across with linear algebra working with matrices is just keeping everything in order. You have a bunch of letters floating around, you have a bunch of numbers floating around. The biggest problem you're really going to run into is, believe it or not, just plain old arithmetic, keeping everything straight. So, okay, let's go ahead and just take the coefficients, make it a matrix, augment it with this series of numbers right here, turn it into reduced row echelon form, and we'll have our solution and see what it is. So our matrix looks like this. We just take the coefficients. We have 1, 1, 2, negative 5, and we have 3. Let me go ahead and put a little, just to show you that these are the coefficients of the variables, and these are the solution set. So we have 2, 5, negative 1, negative 9. We have 2, 1, negative 1, 3. And we have 1, negative 3, 2, and 7. And then negative 3, negative 11, negative 5, negative 3, negative 11, negative 5. This matrix is the one that we want to convert into reduced row echelon form. Okay. So we notice, remember our process, we go ahead and we find the first row that actually, or the first column that has non-zero entries, which is this one, and then we find the first row that has a non-zero entry, which is up here. So this becomes our pivot. Once we find our pivot, we divide everything in that row by that number to turn it into a 1. Well, in this case, it's already a 1, so it's not a problem. So in order to get rid of, the next step is to get rid of this number, this number, this number, to turn everything in that column into a 0. And of course, we do that by, we're going to multiply the first equation by negative 2, add it to the second row. And then we're going to multiply the first row by negative 2, add it to this row. And then the third thing we're going to do is multiply this by negative 1 and add it to this row. And when we do that, we will have converted this column to 0. And then we move over onto the next column. If you want to check out the process, you can go back to the next lesson and review it, where we did it very, very carefully. Each individual pivot, each submatrix, and so forth. I'll go ahead and do just the first conversion. Once I've done these 3, we end up with the following matrix. Of course, the original one doesn't change. We have 1, 1, 2, negative 5, 3. We have 0, 3, negative 5, 1, negative 9, 0, negative 1, negative 5, 13, negative 17, and we have 0, negative 5, negative 2, 17, I think that's a 17, yes, and negative 11. So these are all zeros, and now our this is the entire matrix, our first set of conversions. Now we notice this, so we can leave that alone. Now we just deal with this. So this is all zeros. We move to this column. So this particular column, 3 happens to be the first number that we run across going down. So this becomes our pivot. So our next step would be to divide this entire row by 3 to turn this into a 1, and then do the same process. Multiply this by 1, add it to this row, multiply this row by 5, add it to this row, and so on until we get to reduced row echelon form. Now, I'm going to go ahead and skip the process, and I'm just going to give you the reduced row echelon form, and then I'm going to take a couple of minutes to talk about how it is that we do that and the use of mathematical software to make this much easier for you. So what we end up with is the following matrix. Let me just draw a little arrow here and put an RRE. Our reduced row echelon form, what you end up with is 1, 0, 0, 2, negative 5, 0, 1, 0, negative 3, 2. Excuse me for these little marks that show up. I don't want it to confuse the numbers here. And then we have 0, 0, 1, negative 2, 3, and the final row is going to be a row of all zeros, which is fine. It doesn't matter. So here's our reduced row echelon. Notice 1, 1, 1. These are our entries. It's zeros, the columns. This is not a problem. So this is what we end up with. Now, I want to take a couple of minutes to talk to you about the use of mathematical software. The techniques for what's this called, Gauss-Jordan elimination, turning it into a reduced row echelon form, dealing with the matrices, a lot of the techniques that we're going to be developing are going to be computationally intensive. So it's not a problem if you want to do them by hand. I think it's certainly a good way to get comfortable with the material. But at some point when the matrices start to get big, even as like a 3x3 or 4x4, you definitely want to start using mathematical software to make your life easier. As long as you understand the process originally, it's not a problem after that. Now, there are several math softwares that are available. For example, one of them is Maple. It's one of the oldest. It's the one that I use personally. It's the one that I was trained by. There's something called MathCAD. It's very, very popular in the engineering field. There's something called Mathematica, also a very, very powerful, and these are all symbolic manipulation software, not altogether different than what's available on a TI-89. So if you have a TI-89, you can also do matrices on there because it handles it symbolically as opposed to numerically like older calculators used to do. And there's also something specific called MATLAB, and it stands for Matrix Laboratory. This is specifically for linear algebra. It's also a very, very powerful programming language. So any one of these is fine. Very, very simple to use. You just plug in the matrix, and then you have some pull-down menus or some commands, and you say reduced row echelon, or find the inverse, find the transpose. So you can go from here to here without having to go through all the intense computation. Let the computer do that for you. It's the math that's important, not necessarily the computation. Especially since, like I said before, arithmetic mistakes, when you're dealing with tens and hundreds of numbers, they're going to happen. So just thought I'd throw that out there. Feel free to make use of any of these software, and they're reasonably inexpensive. Okay, so let's get back to our solution. So we have this final reduced row echelon form here. And what it is let me actually go to another page and rewrite it. So I have 1, 0, 0, 2, negative 5, 0, 1, 0, negative 3, 2, 0, 0, 1, negative 2, 3, 0, 0, 0, 0, 0. Oh, by the way, when you're doing entries for a matrix, notice I tend to go in rows. You can also go in columns. What you don't want to do is just sort of start going randomly, putting numbers here and there to fill them in. Believe it or not, that actually creates problems. So be as systematic as possible in all things you do mathematically. So this is a matrix. It's equivalent to the following system. Well, this is x. Okay, so we have x plus 2, and let's say that this variable is w. So we have x, we have y, we have z, we have w, and we have the solutions right here. So we have x plus 2w equals negative 5. We have y minus 3w is equal to 2. We have z minus 2w is equal to 3. Again, it's in the w column. These are the solutions. So now, notice what we have, this system right here. We have an x, y, and a z, and in each case a w shows up. So w becomes a free parameter. That means I can choose any value I want for w, and then I can solve for x, y, and z. So what we have here is infinite solutions. You can stop here if you want. Let me go ahead and show you what this looks like explicitly in terms of x, y, z. In other words, I'm going to solve for x and y and z. Because w is a free parameter, I'm going to put it down here. I'm just going to call it r. You can give it anything you want, okay? So x is going to equal to minus 5 minus 2r. Y is going to equal 2 plus 3r. And z is equal to 3 plus 2r. And these are explicit representations with all of the variables on one side and everything else on the other. This is an implicit, again, it's an implicit relation because you can always solve it for one of the variables. That's all implicit means. These are your solutions, infinite number of solutions. Okay. Also notice something you already noticed this, of course, the column that doesn't have the leading entry, the column where there are multiple entries, those are the columns that are going to be your free parameters. In this particular system, there was only one column like that. All of the other columns had leading entries, and they were all zeros. If you end up having 2 or 3 or 4 columns, you're going to end up having 2 or 3 or 4 different parameters. Speaking of which, let's go ahead and take a look at one. I'll just do the matrix, and then we'll do the reduced row echelon form, save us some time. So we have a system 1, 2, 0, negative 3, 1, 0, 2, 1, 2, 3, 4, 5, 6. 6 variables this last column is always the solution. Okay, so we have x, y, z, s, t, w, something like that. So this is 6 variables that we're dealing with here. 1, 2, 1, negative 3, 1, 2, 3. We have 1, 2, 0, negative 3, 2, 1, 4. And my apologies, my 4s always look like 9s. 3, 6, 1, negative 9, 4, 3, 9. So this is the particular system that we're dealing with. Okay, we have 4 equations, 1, 2, 3, 4, and 6 unknowns. That's our augmented matrix, our solution set. So when we go ahead and convert this using our mathematical software to reduced row echelon form, we get the following. And again, remember, reduced row echelon is unique. So the reduced row echelon that you get is going to be the same as everybody else's. There's only one reduced row echelon form. So we get 1, 2, 0, negative 3, 0, negative 1, 0. We get 0, 0, 1, 0, 0, 2, 1, 0, 0, 0, 0, 1, 1, 2, and we get a row of all zeros. So that's our reduced row echelon form. Let's take a look at the ones with leading entries. We have this one. I'll put an arrow for the ones that have leading entries. Okay. These are going to be the variables that we actually end up solving for. These are not the free parameters. Now, the columns, I'll circle them, that don't have leading entries, that are just kind of randomly arranged. Again, this is reduced row echelon form. It's not a problem. It satisfies the definition. These are going to be your free parameters. So column 1, column 3, column 5, okay, and then column 2, column 4, and column 6, those are going to be your free variables. Those can be anything. So let's go ahead and pick some variables. Let's actually call them, well, since we're dealing with this many, let's just go x1, x2, x3, x4, x5, and x6. So once again, the ones that are going to be free parameters are 2, 4, and 6. So let me circle those, 2, 4, and 6. Okay. Now I should probably move on to the other page. Now the linear system that reduced row echelon form represents is the following. x1 plus 2x2 minus 3x4 minus x6 equals 0. And then we have x3 plus 2x6 equals 1. And then we have x5 plus x6 equals 2. Okay. Now we assign the free parameters. Once again, we said to the 2, 4, and the 6. So we get something like this. x2 is equal to, I'll just say r, could be anything. x4 could be anything, so let's just call it s. And x6, that can equal anything, we'll call it t. Now, x1, just solve that equation. Just move this over there, this over there, this over there, and what you end up with is x1 is equal to t plus 3s minus r. x3, just move this over there. That becomes 1 minus, and we said that x6 is t, so 1 minus 2t, and we solve for x5. This one. We just move this over to that side. That's equal to 2 minus x6, which is t. This is the power of reduced row echelon. Again, use the mathematical software, knock it out, and then just literally read the solution right off. This is the implicit expression of the solutions. This is the explicit expression of the solutions. The reduced row echelon had columns with leading entries. Those are the variables that you solve for. That's these things. At the end, those are conditional. The columns that had variable entries, the non-leading entries, those are the ones that we assign free parameters to. They can be anything you choose. So again, we're dealing with an infinite number of solutions here. Okay. Okay. Let's do another one. We'll do 1, 2, 3, 4, 5, 1, 3, 5, 7, 11, 1, 0, -1, -2, -6. Put it through our mathematical software, we get a reduced row echelon of 1, 0, -1, -2, 0. We get 0, 1, 2, 3, 0. And then we get 0, 0, 0, 0, and 1. Okay, let's take a look at this third row, 0, 0, 0, 0, 1. This basically tells me that, so we know that this is our solution set, and this is our x, x1, x2, x3, x4. This is telling me that 0 times x4 is equal to 1. Well, you know, 0 times anything is equal to 0. It's telling me that 0 equals 1. That is not true. So again, no solution for this system. And reduced row echelon, let us know that. Again, unique solution, infinite number of solutions, no solution. Okay. They also call this an inconsistent system. Okay. I want to talk about homogeneous systems a little bit. So, homogeneous systems are linear systems, of course. Where each equation is equal to 0. That's it. Everything on the right-hand side of the equality sign is just a 0. Homogeneous systems are very, very important in mathematics. They play a very important role in the theory of differential equations. And of course, the theory of differential equations is highly applicable to all fields of engineering and physics. So homogeneous systems, a huge field of research. So an example would be something like 2x plus 3y minus z equals 0, x minus 2y minus 2z equals 0. Notice everything is 0 on the right-hand side. Kind of makes it a lot easier to deal with. Plus 3y minus z equals 0. So that's it. This is just an example of a homogeneous system. It just means that everything on the right-hand side is 0. Now you notice the homogeneous system always has the trivial solution, which means x, y, and z, all the variables are 0. So that's called the trivial solution. We're not too concerned with the trivial solution. X sub I equals 0 for all I. X sub I, meaning x1, x2, x3. Here we have them as x, y, and z. But if you have more than 4 or 5, you just refer to them as x1, 2, 3, 4, 5, 6, like we did in the previous example. And they all equal 0 for all I. This upside down A is a symbol which means for all. Again, just a little bit of formal mathematics. Okay. Now we'll go ahead and we'll give you a theorem, which we won't prove, but which will come in handy. Notice here we have 3 equations, and we have 4 unknowns. Oh, no, I'm sorry. Oh, I can't even count now. No, it's 3 equations and 3 unknowns. So now the theorem says a homogeneous system of m equations in n unknowns always has a non-trivial solution if m is less than n. In other words, if the number of m is the number of equations, so if the number of equations is less than the number of variables, this homogeneous system always has a non-trivial solution. That means there's always at least one solution that is not all zeros. X equals 0, y equals 0, z equals 0, and so on. So let's repeat that. A homogeneous system of m equations and n unknowns always has a non-trivial solution. It doesn't say whether there are infinitely many or one. It just says there at least one exists if m is less than n, if the number of equations is less than the number of unknowns. Let's do an example. Okay. So we have 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 2, 1, 0, 0. When we subject this to Gauss-Jordan elimination, which brings us to reduced row echelon, we end up with the following: 1, 0, 0, 1, 0, 0, 1, 0, negative 1, 0, and 0, 0, 1, 1, 0. Again, this is our solution. This is the entire matrix. So here we're talking about 3 equations, 1, 2, 3, and we have 1, 2, 3, 4 unknowns. This is, of course, the solution set on the right side of the equality sign. So we have more unknowns than equations, and sure enough, the reduced row echelon shows us that, yes, we have leading entry, leading entry, leading entry. So let's call this x, let's call this y, let's call this z. These can be the free parameter. We can call the variable w, so we can set w equal to s and then solve for this. This has a solution. In fact, in this particular case, because we have a free parameter, we have an infinite number of solutions. Okay. Let's go ahead and list these out explicitly. What this says is x plus w equals 0. This says y minus w equals 0. This says z plus w equals 0. So w is our free parameter. So we'll set w equal to s. We'll solve for z. Z equals minus w, which is minus s. Y equals w, which is s. And x equals negative w, which is negative s. This is our explicit solution. This is our implicit solution. You might have a favorite. It's up to you. Personally, I actually prefer the implicit form. I like to do the math myself. When I see it like this, it's perfectly fine. Again, just a personal preference. So, might as well use our erase function here. So again, this is implicit, this is explicit. And there you go, solutions of a homogeneous system, Gauss-Jordan elimination, reduced row echelon, matrices represent linear systems represent matrices. Thank you for joining us at educator.com. We'll see you next time.